Hi everyone. So next PowerPoint video is about electrical power. So we're getting towards the end of the electricity unit. This lesson, and then there's a couple of weeks worth of electronic stuff, and then that's us going to have finished electricity. So let's focus on today, electrical power. And basically power or electrical power or power in general is about the rate of using energy. So we just read through the text here. It says appliances in the home convert electrical energy into other forms. So a TV, for example, converts the electrical energy into light and sound. Washing machine produces kinetic energy or movement energy and heat and sound as well. And this stuff in red is kind of the relevant bit that we're going to talk about. The rate at which an appliance uses energy is termed their power. So whenever it talks about the rate of something, it means with respect to time. So power is the amount of energy used in a given time. So for physics, we talk about per second. So if an appliance uses 1 joule of energy every second, then we say it's got a power of 1 watt. And we'll come back to the units and stuff like that a bit later on. And generally, the high energy devices, like things that produce heat, toasters, cookers, kettles, hair dryers, etc., they have a higher power rating than, say, a TV or a lamp or whatever, because they don't produce as much heat. Generally, things that produce a lot of heat will have a power rating of over 1,000 watts or 1 kilowatt. So there's a general equation to calculate power, which is power equals energy over time, or P equals E over T. Remembering that power is measured in watts, energy is measured in joules, and time is measured in seconds. So we'll do a wee quick worked example here. So it says we've got an electric heater with an output power of 1 kilowatt. It's switched on for 5 minutes. Calculate the energy from, or the energy output from the heater. Now, I've said this every single time and I'll say it again. When we're doing these questions about electrical power or power in general, there's a number of equations that you might get mixed up with. So the standard thing, the first thing you've got to do is transfer the information from the question with the correct symbol. Just put it on the left-hand side of your page there. So we know we're told in the question the power is 1 kilowatt. So we have to have the power in watts. So we're changing the 1 kilowatt to 1,000 watts. Energy is what we're asked to find. So we're going to put a question mark next to that. And then the other thing we need to remember to do is convert the 5 minutes into seconds, which is 300 seconds. Next thing, first mark you get is for picking the correct formula. So we know from doing this on the left-hand side what's power, energy, time. So that should point you to this equation here. Substitute in the numbers. So the power is 1,000 equals E over 300. So, and really what we're going to do here now is cross multiplying. You just got to remember that the 1,000, it really just means 1,000 over 1. So if you do E times 1 will equal 1,000 times 300. So we're rearranging the subject of the equation to give us that E equals 1,000 times 300, which hopefully works out to be 300,000 joules. And that's your answer for that. Dead straightforward, no problems at all. In general, power calculations, etc., are just standard calculations. There's a couple of complications in the last two, but we'll get to that when we do it. So that formula we've just been doing, the power equals energy over time, is general power equation. It works with mechanical energy, like kinetic energy and potential energy and stuff like that as well. But the next three equations we're going to learn about is to do with specifically electrical power, and it's going to involve voltage, current, and resistance of an appliance, or two of the three in each equation, as you're going to see. So the first one is that electrical power can be given by the current multiplied by the voltage, or to write that with symbols, it's P equals IV. Remember, capital I is the symbol for current. And again, remembering that power is measured in watts, current should be in amps, not milliamps or microamps, and voltage should be in volts, not kilovolts, etc., etc. So a wee worked example says the calculate the current drawn by a 805 watt electric toaster. So 805 is a kind of weird value, but I think the reason for that is you'll find out at the end when we calculate the thing we want to calculate, the current that is. So again, first thing we do is we write down the information we've got from the question. Now, I've done this one deliberately because it's asking for the current, so that's going to be I equals question mark. We know the power is 805, and then it tells you it's connected to UK mains electricity. Now that's kind of a code thing that you have to recognise or realise that when we're talking about UK mains electricity, the voltage of UK mains electricity is 230 volts. So when you first look at this question, it doesn't look like you've got enough information, but that's a learning outcome. You need to know that the mains voltage in the UK is 230 volts. It does vary in other countries, but generally you're only going to be asked about the UK. So put down the equation, substitute in the numbers. So it's 805 equals I times 230. So rearranging, get the subject to the formula. I would be 805 divided by 230, which gives us an answer of exactly 3.5 amps, which is probably why the 805 watts was used in this question. Okay, so that's the first electrical power equation. And the way you know how to use which one you're going to use is this. So it's crucial you always write down what you're given in the question, and that's going to point you towards the correct equation. Just a wee quick thing about this picture here. This image is of what's called a rating plate. Every appliance that's sold in the UK, probably Europe-wide, I'm not sure, must have a rating plate on it. And the rating plate will give what voltage it should be used at, it gives the frequency of the AC, the power, and there'll be other information on there like not to be used in bathrooms, so it's probably something to do with a hairdryer or something like that, possibly. So the formula that we've just been learning about enables you to calculate the correct value of fuse that can be chosen. Now at the end of this PowerPoint there's another wee bit about fuses. You don't need to know a huge amount about fuses, just as a protective device. All plugs have got them. Most appliances might have internal fuses, and it protects the appliance from overheating or the flex overheating, and so on and so forth. So the next equation is going to link power, current and resistance. The previous one was, remember, current and voltage. So this one is going to measure or link the power with current and resistance. And it's a bit more complicated because there's a squared term. So the formula is power equals current squared times resistance, or P equals I squared R, where the usual things apply. Power is in watts, current is in amps, and this time resistance is measured in ohms. Another worked example, so we've got an iron this time. It's got a resistance, the element of the iron has got a resistance of 76, and there's a power rating of 690, and this time they want to find the current. Now we've deliberately went to a more complicated question because we want to find I, okay? So, don't want to keep repeating myself, but I'm going to keep repeating myself. The first thing you have to do is get the information from the question, put it down with the symbols, and in this case we want to find the current, so that's the question mark. Everything else is there, but it's all in watts or ohms, so we don't need to do any conversions from kilo ohms or kilowatts, etc. First mark is for writing down the equation. You then substitute in the numbers in the correct place. So the power is 690, so that goes there. I squared is the thing, the unknown, the resistance is 76. So then you rearrange the subject of the equation. So it gives us that I squared equals 690 divided by 76, which I've missed that line out there, but you could have written down or worked out what 690 divided by 76 is. I think it works out to be 9.1, but that's what I squared is, and that's a common mistake that people leave it at that stage. You have to remember to take the square root, which rounds to, I think it's 3.0 something or other, but so it just rounds to 3 amps. So that's the kind of the complication you have when it's got the squared term involved. Okay, the last electrical power equation is one that's probably used the least. I've done these 3 equations in the kind of order that they'll be used the most, perhaps. So this one, for whatever reason, is used the least probably. It's the one that links power, voltage, and resistance. And it is that power equals voltage squared over resistance, or P equals V squared over R. Now, you get these equations from combining P equals VI or IV with Ohm's law of V equals IR. I don't think there's any need for you to understand where we get these. I think you just need to be able to recognize them and be able to use them. Again, standard thing, powers and watts, volts and voltages and volts, resistance in ohms. Another worked example. Here we've got an LED torch, and it's got a lighting circuit which has got a resistance of 18 ohms, and it's an LED torch, so it's going to have a really low power output, only 2 watts, and we have to calculate the voltage of the power supply. In this case, it's going to be a battery or batteries. So standard thing, copy down the information with the correct symbols on the left-hand side. And that's going to point you to hopefully the right equation. So it's PVR. You look up your formula sheet, find the formula that relates to PV and R, and hopefully you find that it's P equals V squared over R. Substitute in the numbers, so it's 2 equals V squared over 18. Cross multiplying, so the 2 is 2 over 1, so V squared is going to be 2 times 18, which is 36. And again, that's a common mistake. People will stop at that point, but that's what V squared is. So V will be the square root of 36, which hopefully if my maths is correct, works out to be 6 volts. Okay, and that's the 3 equations, the electrical equations, electrical power equations, along with the power equals energy over time general equation. And so the key thing is getting the information from each question, putting it down with the symbol, and then figuring out the right equation from that. Bear in mind, closely linked to all of this is Ohm's law equation, V equals IR. So bear in mind, you may have to kind of chop and change between equations and also use Ohm's law. Okay, last thing is a bit more about fuses. So that's where the fuse is in a mains plug in the UK. And that's what it looks like, or can look like. The ones you get usually are ceramic, so you can't see it, but basically what a fuse is just a wee thin piece of wire. There's a symbol for a fuse. It doesn't look unlike the actual thing that a fuse is like. And it consists of a thin strand of wire with 2 electrical contacts. It goes into the live wire in the plug, and it's there as a protective device to prevent the flex from overheating. A lot of people think it's to protect the appliance. It's not. It's to protect the flex from overheating. If you don't have a fuse, then what can happen is the wire gets too much current going through it and it melts and goes on fire. If you have a fuse and too much current flows through the fuse, the wee wire will melt or blow and it cuts off the supply of electricity. So the flex is there to stop, the fuse is there to prevent the flex from overheating or catching fire. Now, it's important that a correct size of fuse is fitted into a plug. It should normally be the next value of the fuse that's available above the normal current of the appliance. So you could calculate the current if you knew the power and the voltage. And say, for example, if an appliance normally used a current of 2.4 amps, then the fuse you would go for the fuse directly above that, which would be 3 amps. And that would be the best to fit. And the last thing is that there is a general rule, this is in the learning outcomes, that if your appliance that is connected up to the mains electricity has a power rating of less than 720 watts, then you use a 3 amp fuse. If the appliance is more than 720 amps, then you use a 13 amp fuse. There are other values of fuses available, but generally at NAT 5 they really just talk about 3 amps and 13 amps. Okay, so that's this one, reasonably short one, hopefully. PowerPoint that is. So it's normal stuff again. I'll post questions that you have to do, and then on Thursday there'll be a quiz that you have to complete. But generally this stuff is straightforward and it's just number crunching, so fingers crossed you do okay. Okay, that's me finished for today, and I'll catch you next time.